Hey everyone, let's have a question from the Blind 75 series today. Okay, so this question is called Clone Graph. It's on Leetcode. It's a medium level graph question. So yeah, let's first look at the question. It's saying we should return a deep copy of the graph, and the graph has a value and list of neighbors, which is a list of nodes in the graph, right? And here's an important point, I think, to note. Each node's value is the same as the node's index. For example, the first node with val is equal to 1, the second node with val is equal to 2, and so on. The graph is represented in the test case using an adjacency list. So first of all, I'll explain you the different types of copy that we can have. We can have two types of copies, which is shallow copy and deep copy, right? So I'll show you what both of them mean with an example. So if you consider an array and A is equal to 1 to some elements, right? Then to do a shallow copy, all I have to do is say B is equal to A. So this is a shallow copy. What do I mean by shallow copy? Is that we're just storing the reference of A into B, right? So what that means is if I modify B, for example, then A, whatever A is pointing to will also change because B and A are pointing to the same thing. So 3 would be 7, right? So that's what it means by a shallow copy. So now, how to do a deep copy? So for an array, it's pretty easy, right? If you just say C is equal to, this is in Python. Then C is a deep copy. What this means is that even if I modify C, A will not change. Right. Okay. So now that we know what both of them, what deep copy actually means, we can get started on how we can do this for a graph. So this is a Leetcode medium level question, so it won't be as easy as it was for an array where we just did this. So the graph here is represented as an adjacency list. If we take an example graph, so 1, 2, and 3, they'll give us any one node as the input in the graph, right? For example, they might give us 1 or they can give us 2 on any of these nodes. So essentially this graph is like there's node 1 and 1 with value 1 and neighbors 2 and 3, and these neighbors are not integers, right? They are actually nodes. So this is node 2, which is representing this 2 node 3, right? That was my mistake. Okay. Yeah. And then if you say node 2, it has value 2 and its neighbor is node 1. Node 3, value 3, neighbor is node 1. So what they want us to return is, essentially they want us to return the deep copy, right? So that means that they need a new node 1 with value 1, a new node 2, a new node 3, showing, symbolizing that 2 and 3 are neighbors of 1, new node 2 with value 2, and neighbor new node 1, new node 3 with value 3, and again neighbor new node 1. So what is difficult about this is, like, you might make a mistake about this, is that you'll have to keep track if you've allocated space for a particular node or not. If suppose I am exploring this particular node 1, just a second. Yeah. If I'm exploring node 1 and I've allocated, first of all, I've allocated memory space over node 1 and I came across 2. I've allocated memory space for node 2 using some traversal technique. It can be BFS or DFS, right? And I've come across 2 and I allocated some space for 2 and added it to the neighbors list of node 1. I encountered 3. I added the new node that I've allocated, for example, new node 3 to the neighbors list of node 1. Now, after exploring 1, now I will start to explore 2. So 2 might have more neighbors, right? In our simple example, it doesn't, but it will. There might be more complicated graphs. So now I want to add, what I should do is, first of all, I should not allocate a new node for 2 because we already allocated it in the previous step when we were exploring node 1. So I should just add the node 1 to the neighboring list of node 2. But we already allocated space for node 1, right? So we have to add that particular reference only to the neighbor list. So how we can solve this, to keep track if we've allocated the space for this particular node before or not, is by the use of a hash map, right? So how this works and why this works is, it was written just in the question that the node has the same value as the node's index. That means that we cannot have two nodes with the same value. So we're safe to use the node's value as the key in our hash map. So that's it. If you understand this part, then the rest of the code will be pretty easy. So let's take a look at it. The first two lines, these two lines, I'm just checking if the graph is empty. If the graph is empty, the deep copy of it is empty. So we just return that. We just return none. And so I'm using BFS over here. I have the visited hash map. So this visited hash map is special because it does not just store if we visited a particular node or not. It also stores for that particular node value what is the node space that we've allocated, right? And this is the queue, which we're starting off with the whatever node that they've given over here. I told you, right? They will give you any node in the graph and you have to return its deep copy. So we're initializing this visited hash map with the current node, whatever node they've given with its value, and storing the newly allocated node over here. So just like in BFS, which will iterate until the queue is empty, and we'll pop the first element in the queue, and we will retrieve the the pointer to the whatever we allocated it before. For example, we'll start off with node, whatever node that they've given, we'll pop it. So C will be equal to node, and C1 will point to whichever memory location this is, right? So we will know which node was allocated, which was a memory allocated to this particular value of node using this hash map, right? So now we are going through the neighbors of the original graph, because for now, even if we have C1, we do not know what are C1's neighbors because we've not made the deep copy yet. We do know C's neighbors. And so yeah, what I'm appending in the queue is the, nodes of the original graph because we want to explore it, right? So we need to know its neighbors. So we know its neighbors and we're exploring them. And over here, we're checking if we visited a particular node or not. If we visited the node, if we've not visited the node, then we're adding it to the queue. Because if we do not have this condition, obviously, in BFS that we will loop forever because of cycles, right? And so here the condition is like, if we've not visited that node, it also means that we've not allocated it any space. So in this line of code, we're allocating the space, right? And we're adding it to the hash map, keeping it track using the value of that node. And for all of the neighbors, we're going to be appending it to the new node. For example, if we're visiting 1 in our previous example, so we will be appending both node 2 and node 3 to the list of neighbors of C1, which is the new node. So how are we getting, we're not just appending, the neighbors. So I can just append n over here, but that would be wrong because we have to append the newly allocated nodes, right? So that's why we're using the hash map again to retrieve those nodes. So that's it. This whole code will make the, deep copy, and we're returning the node that they've given us before using the hash map. Yep. This should run. Yeah. So that's it. I hope my explanation made sense and that you understood it and that it'll help you solve more graph problems. Thank you for watching.